So in the previous segment we stopped here saying that this is the pressure amplitude of the standing wave which exists on the left hand side from where the wave was impinging on the wall, and theta and B will be decided by the impedance of the wall which actually is trying to stop the wave. That is the story till now. And yeah, then we were talking about how we can use this to measure impedance. So what's done is, suppose you have a tube like that, and here you have this speaker, which is producing this sound field. Okay, and then you have the material for which you want the impedance to be measured. Okay, so what is done is a small hole is made on that. Okay, and then through that a microphone is sent horizontally. Okay, at the end of this there is a microphone, small microphone, and then you traverse it throughout the length. Again, is it visible? Yeah, there it is. And then you keep on measuring the pressure values, and you see this, you are trying to measure the amplitudes. So something called SWR, okay, standing wave ratio, you try to measure, and they are A1 B1 minus B1. So the ratio of can you tell me what these are, what these two values are? This is the pressure amplitude of the antinode. See this, when this term goes to 0, this will be maximizing, and A1 plus B1 is the amplitude of the antinode where the pressure is maximum, and when this term goes to 0, this one will be the pressure amplitude of the node point. Okay, so that is why it is called the standing wave ratio. It is the ratio of the pressures. So you can write it here. So it is the pressure amplitude at antinode, and this is the pressure amplitude at node. Okay, that means you are traversing and you are plotting the values of pressure amplitudes, and whenever you see the maximum, then that gives you A1 plus B1, and where you see the minimum, you will get A1 minus B1. Then once you get this, from here you can get B1 over A1 is equal to minus 1 by SWR plus 1. So this is the ratio which you can get, and knowing A1 you can calculate B1. Okay, so because as I said, A1 was the input, so it's known to us. Fine. Then so one part is done. So how to calculate theta? So for that, what is done is, from this end you traverse and try to see the first node where it happens. Okay, that means this one will become 1 at that location, right? Because that's the maximum value you are getting. Sine theta, sine of this is 1, because this term has gone away, because this is 0, so it's not there. So that is why you are getting this value, right, at node as pressure amplitude. So that's why this one, the sine square term will go to 1, and from there what you can get is, if you replace that, that means, see, you are substituting k1x plus theta over 2 to be minus pi over 2, because see, you remember the formulation which we had derived, in that x positive was on that side and 0 was at that location, and x always positive on that side, and this side it was negative. So x positive, again it will not be visible, I will write here, okay, x positive, and here x negative. And that is why for the first node you are replacing this, and from here k1 is again that 2 pi over lambda 1. So you are getting this, theta is minus pi minus 2 k1x. Okay. Now x is that position where you actually got that minimum value. Okay. So you saw that from here you got theta, from here you got B1. So then you can get impedance of that particular thing. Once you know impedance, you can calculate reflection coefficient, transmission coefficient, everything. Okay. So just as an example, if you have SWR value of 2, and suppose you conducted that experiment, and the first node location, okay, I'll write as x of first node happens to be at say 3/8 of lambda. Okay, lambda also you can get from that curve at if you plot it. Okay, then the theta you are getting to be minus pi over 2 by using that formula. So here, in place of k1 you will put 2 pi over lambda, and x is given to be 3 lambda over 8, and you will get it. And from there you can calculate that a1 over 3 e raised to I pi over 2. Okay. And your z n will come out to be 0.8 plus j 0.6 rho 1 C1. Okay. So that's how you evaluate impedances of any material by putting inside that traversing microphone setup. Okay. Yep. So here we will stop this segment which we came to discuss about this standing wave pattern and its application. Okay. We'll see in the next segment, where what we are going to do is, this was almost like the discussion on two fluids when they are interacting, and one of that fluid you can now consider as a solid also by using its equivalent rho c value, by using c to be the bulk velocity inside the solid. So that's the one line summary in a way of what we discussed now in this segment. Now in the next segment, what we are going to do is, we will keep this as a finite. So it will be say fluid 1, this will be fluid 2, and now we will have fluid 3. Now why it is important is, remember I just told you now that the previous case is helpful in finding out the reflection coefficient considering that this wall is extending to a long distance, but that is not generally the case. So we will have finite thickness of the wall. So if we are now able to understand this phenomena, we can replace the same thing here, this solid as a fluid, equivalent fluid, and we can talk about what is the transmission coefficient, what is the reflection coefficient of these finite thickness walls. That means then you can in fact predict if some sound field is existing here, what will be the sound field in the adjacent room if a particular wall is put there. Okay, so that's what we are going to see in the next segment. See you in the next segment.